I want to use the remainder time just to give you a few more examples of this recurrence, solving recurrences. Okay, as I said that this comes naturally from recursive algorithm. Next time for sorting, we're going to see yet another recursive algorithm and its time complexity. Okay, but here let's just go through some examples. I'm not going to give the real algorithm, but just the recurrence itself, and we want to how to solve that efficiently. Okay, all right. So here's one example, but in this example, I'm not writing out the base cases explicitly. Okay, I simply give you this relation with the assumption. So under the assumption that you always assume that the t of some constant is. So that's always the base case that we're not writing for constant c prime. Say c prime can be equal to 1, 2, any constant, okay? So this is always the base cases that I'm not writing. Namely, when your problem size is constant, then the time complexity is constant. Okay, so I just write the recurrence part. Okay, all right, let's look at this recurrence. In fact, this one looks very similar to the one we just did for the binary search. In binary search, we have that t of n equal to t of n over 2 plus constant. Remember, that was binary search. Here, what I have is that t of n equal to t of n over 3 plus a constant. Okay, so let's see what is the time complexity for this case. Okay, all right. Well, remember, first we unroll for a few iterations to see whether we see a pattern. So this is the original recurrence, and applying the original recurrence relation to this. So we know that the t of n over 3 equal to, equal to t of whatever size here divided by 3. That means that it's t of 9, which I can also write as t of n over 3 divided by another 3. That's 3 times 3, that's 3 squared. It's the same. It's just that this way of writing make it sometimes easier to see the pattern. Okay, so what we have is that after the first unrolling, I have t of n over 3 squared plus c plus c. So this portion is the same as t of n over 3. Okay, so we replace t of n over 3 by this quantity, this relation. Okay, by this applying the recurrence relation. Okay, all right, so that's the first step. Now we do it again. We say that we don't like this. Let's see what we can do. Well, we know how to use this recurrence relation to make this even smaller. It depends on problem size, even smaller. In particular, we know that t of n over 3 squared equal to, for whatever the size here, I divide by yet another factor of 3. So you already have 2. If you divide by another factor of 3, we have 3 to the power of 3 now, plus c. Okay, so plugging in here. So now we plug this in. We have t of n over 3 cubed plus c. The c is here. And I also have the 2 old c. They still need to come down. Okay, so now I have 3 c additive terms hanging there. Okay, if you do it one more time, then on the denominator, because the size is going to divide by another factor of 3. That means that in the denominator, you're going to multiply another factor of 3. So now from 3 cubed, you're going to get 3 to the 4th plus c. You're going to also, outside, you're going to get another c. And you also have the old 3 coming. Okay, now the pattern becomes clear. Every time I do this unrolling, if I do this k times, that means in the denominator, I have to multiply 3 k times. Okay, you multiply that k times, that means that the exponent is 3 to the k, because you basically denominator is at n 3 times 3 times 3 k times. That's why this is n to the divided over 3 to the power of k. Okay, so and then outside, what do I have? Each time I do the unrolling, I add another c. So after I do this k times, we have c times k. Okay, very similar to what we see earlier. Okay, all right. Now what do we have? Okay, so, oops, it's still not very clean. Okay, now we need to know when we stop. Okay, we stop when this become constant. Okay, so we write it here. We say that we stop when n to the 3 to the k, namely what's inside. You want this to be constant, equal to 1. Okay, so that means that 3k equal to n. That means that k equal to log n, but base 3. Okay, this is when we stop. So we plug it in here. We stop when n over 3 k is 1, that's t of 1, plus c times k, and the k equal to log n base 3, so that's c. Asymptotically, what's this? Well, we know this is constant. So constant plus something which is logarithmic. This is a dominating term. The second one is dominating term. So what we have is again log n, same as the binary search case. Okay, so even though the recurrence look different, for the binary search case, here we have divide over 2. Now we have divide over 3. But the final asymptotic time complexity remains to be log n. Okay, in fact, this is not too surprising. Okay, so let's actually look back to see why we get the logarithmic running time for the binary case. So you start with size m. Every time I do a recursive call, the size become half of the previous one. Okay, so now the size, that means that to get to constant, this is essentially a geometric series. You can only perform this half logarithmic number of times. Okay, and each time you only take constant other than the recursive call. Okay, that's why that at each step you take constant and you have to do this logarithmic number of times. So the total time, that's basic constant times logarithmic, which is log n. Okay, now instead of say each time I cut it by half, each time we take only 1/3, we cut even more significantly. Okay, but still this is a constant fraction of the original size. Okay, so every time the problem size become only a constant fraction of before, but each time it reduces very fast. You again have a geometric series. Okay, the number of steps you take to reach to a constant is only logarithmic, depends on how much you cut each time, the constant. Okay, so since all the logarithmic function or log n base a is the same asymptotically as log n base b for any different bases. Okay, so remember that we had log n base a equal to log n base b for any constant b that's bigger than 1. Okay, so as long as these are constant, okay, then we know that all the logarithmics. So the precise steps is actually this one is log n base 3, while for the binary search is log n base 2. So this is actually a bit faster, okay, because if you every time reduce only to 1/3 of the size, you cut down even faster. But asymptotically, both are big theta of log n. Okay, so this should have the same time complexity, asymptotic. All right, so that's the first example. So let me quickly go to a second one, which is a bit more complicated than the previous one. Okay, then I'll stop here. Okay, all right. So okay, let's look at this. We again do the same. we say that let's first unroll it a few times, okay? This we have to apply this, the relation to T of n over 2. So let's scratch this out. What is this relation? This relation is saying that given any size, then that equal to the size divided by 2, but the cost I'm going to have is also depends on the size, okay? So if I apply this to T of n over 2, what do we get? This equal to T of inside the size has to become half, which is n over 4. Outside, I have to add a cost, which is the size. It's not n anymore. It's whatever the size is here. So that's n over 2. This is the key, okay? So now the same relation means that T of n over 2 equals to T of n over 4 plus n over 2 now. So now I replace T of n over 2 using this relation we just saw. That gives me T of n over 4 plus n over 2 plus the original n. So this n is this n, and the T of n over 2 is replaced by this. Okay, in other words, let me just write it out. This is T of n over 4 plus n over 2 plus n. Okay, so this now looks a bit complicated. Okay, but no worry, let's try to do this unrolling a few more times. Okay, let's now try to replace T of n over 4. Well, the only way we know is that to apply the same recurrence relation to this again. What do I have? T of n over 4. If I apply this relation, it says that it's the same as the size has to be cut by half yet again. Okay? And outside, I am adding this size, the current problem size, which is n over 4 now. Okay? So now you use this recurrence relation to help you to replace T of n over 4. What do we get? We get T of n over 8 plus n over 4. This is T of n over 4. Okay, now we need to still add whatever remainder terms here, n over 2 plus n. Okay, all right. Maybe let's just do one more time. Okay, so if I now replace T of n over 8, T of n over 8, again, inside, every time we do this, inside the size got cut by half. Outside, I add this current size of the problem. This is what we have. So I have T of n over 16 plus n over 8 plus n over 4 plus n over 2 plus n. Okay? All right. This may not be, this looks a bit hard to see the pattern, but maybe let me actually first write this in the, instead of 16, let's write in the power of 2. Okay? Why? What we said so far is that every time inside is divided by 2, 16 is 2 to the 4, to the power 4. And outside, what do we have? We have n divided over 2 cubed plus n over 2 squared plus n over 2 plus n. That's what we have. Okay? All right? Okay. I hope now it become a bit easier to see the pattern. What do I have here? Well, as we said, every time when I unroll it one more time, inside this T, hold on just for a second. Inside the parentheses, we have that the problem size get divided by yet another factor of 2. That means in the denominator, we multiply by another factor of 2. Okay, so I'm going to write this here. I don't have space. So this equal to, every time, if I do this k times, that means in the denominator, I have to multiply 2 k times, because every time the size gets half, same as before, okay? Outside, what happened? Well, originally, I only have a factor n, okay? The first time I unroll it, I have to add a factor n over 2. Okay. The second time I unroll it, the problem size become half again. So I have to add that term, which is n over 2 squared. Okay. And the third time I have to add n to the n cubed. And till in the time when we get to the case time, this come from the problem size was k minus 1. You see here the exponent differ by 1. Okay, so this is what we have. This is basically the term that the Hanning additive term come from here. Okay, you see this 2 differ by a factor of 2. Okay, so this is our general formula. Okay, so this is the original term, the one coming from the first enrolling, second enrolling, and so on. Okay. Okay. Now, when do we stop? Same story. We stop when you stop, it's always determined only by here. It's not this. What's happening here has nothing to do with your stopping criteria. You stop when what's inside the parenthesis for t become constant because you don't have to. That means you don't have to recursively expand it anymore. Now you know how to solve it. Okay, because t of 1 is constant. So you stop when n over 2 to the k become say a specific constant, say 1. That means that n equal to 2k. That means that k equal to log n over 2. Now you plug in this here. That means we stop 1. N over 2k equal to 1. So inside it become 1. Outside we have m plus n to the set plus n to the 2 to the power of log n over 2 minus 1. Okay. All right. So this is when we stop. Okay. This looks complicated. However, what is this? If I take n out, what do I have inside? Inside I have 1 plus 1 over 2 plus 1 over 2 squared plus all the way 1 over 2 to the power of log n minus 1. What is this? This is exactly geometric series. Okay, I actually don't really care what's here. I know geometric series, the geometric sum, this whole sum is bounded by a constant. Okay, so this is only constant. So what we have is a such constant plus n times constant. So we have linear time for this. Okay, again, geometric series 1 plus r squared all the way to any. Okay, for any m. We know that this is a constant if r is smaller than 1 bigger than 0. Okay, so in this case, r equal to 1/2 because you're getting, even though you have many terms, even though you have logarithmic number of terms, but it decreases so fast so that when you sum them all up, it's still only bounded by a constant, the biggest one here. Okay, so the solution for this is linear. Okay. All right. So this is the example I want to. Okay. So my time is already up. I think that I'm just going to write this one down, also record it, but feel free to leave if you need to. Feel free to leave. Okay. I just continue, finish, and record it. I want to also give an example of a different type of recurrence. Okay. You're going to have some homework problem also of this form. Okay. But the idea remains the same. Okay, it's just how you just keep unrolling it till you find a pattern, and then you find out when to stop, and then you plug it in. That's it. Okay, so let's look at the following example where t of n equal to t of n minus 1 plus c. So this is actually very easy. Unrolling is much easier because if I apply the same recurrence to this, what do I have? I have that inside I reduce by 1. n minus 1 minus 1, that's the same as n minus 2. Outside, I need to add c plus the original c. In other words, I'm applying this relation. So this is T of n minus 1, and this C is the original C. Okay, then I repeat. I do the one more time. If I do the one more time, this T of n over 2 now is replaced by T of n minus 3 plus C. And then I have this 2C from before. Okay, what do I see? Well, we see that if I do, call this one the first time, this is the second time. If I do for the case time, what do I have? We have that inside every time you take away another one. So if I do the K times, then I take away only K, right? Outside, what do I have? Every time you expand, you add another C. So if I do the K times, outside I have C times K. Okay? And when do we stop? We stop when, again, it's only this decides when you stop, when n minus k becomes, say, constant. Okay, so k equal to n minus 1. So we write it in. So this becomes 1, that's T of 1, plus C times K. This means that the K is n minus 1. So this is another constant plus C n minus 1. So constant plus constant times n minus 1, that's dominating term, is this linear term. So we have the solution for this. Oops. Is that's what we have. Okay. All right. Now, in the slide, I also give you another one. What if it's instead of n minus 1, I have n minus 3? Okay. So let me just quickly write it out. Well, we do the same. The first time this is the first time. The next time I enroll this, I get n minus 3 times 2 because I have to take another 3. Outside, I have another extra term of C. So if I do it one more time, that becomes n minus 3 times 2 minus 3 plus C plus C plus C. But this is just the n minus 3 times 3. And if you do it one more time, inside becomes n minus 3 times 4. And you figure out the pattern is that every time you enroll one more time, inside you have to take 3 away. So if you do this K times, so inside you have to subtract 3 times K, because every time you take 3, so that inside you have to subtract 3K. And outside, every time you enroll it, you add another C. If you do this K time, outside you add CK times. So this is what we have, okay? And this stops when inside become 1, n minus 3k equal to 1 means k equal to n minus 1 divided by 3. So that means that this becomes T of 1 plus C times n minus 1 divided by 3. Again, constant. This is n over 3, which is the order of n. So the whole thing is dominated by order of n. So we have. So whether you are subtracting 1 or subtracting 3 away, asymptotically, these two recurrences have the same asymptotic solution. Both cases, T of n equal to big theta of n. Okay? All right, I think that's all that I want to talk about today. And